The presenter today for AVS seminar is Professor Huan Zhang. Professor Zhang is an assistant professor at the Department of Electrical and Computer Engineering at the University of Illinois at Urbana-Champaign. He obtained his PhD degree in computer science from UCLA in 2020 and bachelor's degree at Zhejiang University in 2012. His research aims to build trustworthy AI systems that can be safely and reliably used in mission-critical tasks, with a focus on using formal verification techniques to give probable worst-case performance guarantees. Professor Zhang has received multiple awards for his research work, some of which are, for example, Schmidt Futures AI 2050 Early Career Fellowship, and also multiple competition awards, such as International Verification of Neural Networks competition in 2021, 22, and 23. Yeah, please, please start your presentation then.
Yeah, thank you, Jerry. I'm very happy to have this talk and to introduce my work on neural net verification, the alpha beta quantum framework for form verification of neural networks. And today I especially want to introduce some applications in control and planning that I feel like some of the audience might be interested in. So thank you again for introducing me, and thank you again for inviting me to this excellent seminar. So I guess everybody knows how successful AI are these days. But I want to start make my talk with some issues with those AI models, in particular deep neural networks. So this is something you probably already know. It's called adversarial examples, where people find that, okay, if you add some small perturbations to the input of your neural network, actually it can make some surprising mistakes. So for example, this is the image of a stop sign, and you might need to recognize this stop sign in autonomous cars. And some researchers have shown that, okay, if you have put some stickers on the stop sign image, the neural network, which could highly confidently predict, okay, this is a speed limit sign, not a stop sign. So another relevant research is from my research about robustness on deep reinforcement learning, where what we are doing is actually we are using neural network to run this little robot. You have to know the current state of the system, and you can do that by using some sensors, for example, the velocity, locations, and so on. And we can add some small noise to those sensors, so this is the observations of the agents, and we can make the agents doing something completely wrong. We can make the agent stop moving or actually moving backwards. So we can just by adding some small adversarial noise, we can make the system completely wrong. So that means actually, although deep learning and neural networks, they are successful in many scenarios, they are fragile and actually very prone to errors in some situations, particularly if they're facing adversarial inputs. That means if you have some scenarios where you have attackers who want to destroy the system with those kind of mistakes. And if you look at the news, actually there are all different kinds of problems people found in AI, such as in healthcare, in recruiting systems, in autonomous vehicles, and also even in ChatGPT. I think there are a lot of issues like hallucination, and people are discovering all kinds of issues in AI models these days. And in general, we see that AI models are kind of lack of trustworthiness. You are not going to trust the AI model if you're going to use it in a mission critical system such as an aircraft. you'll think about, okay, the AI system could make some mistakes, like just the stop sign image I showed you. If we encounter certain kind of input, actually it could make some surprising mistakes. And that's what my research is about. I want to give the AI models some guarantees, at least the AI models can do correctly in some scenarios. So those are the outline of my talk today. I will introduce the concept of formal verification of neural networks, which basically can give you some formal guarantees for the performance of neural networks. And also, I will introduce a framework of doing this called Alpha Beta Cron, which is a tool developed in my group for a couple of years, and it's based on the linear bound propagation algorithm. And I briefly introduce how that algorithm works and how we achieve this goal of doing formal verification. And in particular, today I will talk about some applications uh, to control and planning, including formal reachability and the optimal stability analysis to neural network controllers, and also planning, model-based planning with neural dynamics models. So I will first start introduce the setting, the goal of formal verification. So what we are trying to do here is assuming we are seeing this stop sign image, and we know the neural network could make some mistakes, and we want to show that, okay, such mistakes won't happen. We want to show that, okay, this neural network will never predict the image as a stop sign image, as a speed limit sign image. That's the overall goal we want to do. But of course, that's a very challenging task. And in this talk, I will use a very simplified setting that just trying to make the things as simple as possible. Let's see, this is a stop sign image, and this image would normally be classified as stop sign because usually the neural network would output scores for different classes. For example, here the scores for stop sign is 0.9, and score for this image being a split limit sign is 0.1. And here the top point prediction is a stop sign. But now we assume that there's an attacker, and the attacker can actually do some arbitrary change to part of this stop sign. So, and the goal of this attacker is of course trying to make the neural network classify this image from a stop sign to a speed limit sign. And here you can see we define a function called fx, which is basically a difference between the two values, 0.9 and 0.1. If fx, the gap, is greater than 0, for whatever things the attacker put on here, you see here, we assume attacker can put anything here. This is just a small sticker. No matter what you put on the sticker, it doesn't affect the fact that this is a stop sign image. But the attacker actually has a lot of freedom. It can color this small patch to anything they want. And we want to show that no matter what the attacker do, there's no other examples, or mathematically want to show that this function fx is greater than 0. So this is a very simplified problem setting for a setting we want to verify. We want to formally verify that there's no other examples, or mathematically equivalent to the setting of fx is greater than 0. And more rigorously, I write the condition like this. So we define a set S, which defines all the possible pixel perturbations. So here, basically, that means the attacker can arbitrarily change whatever inside this small region. So you can color this small region using different kind of colors, so checkboards, or even you can add words here. Doesn't really matter, and you can change this small part. There's a lot of different possible pixel perturbations you can add here, but I want to prove that for any x belongs to this set S, fx is greater than 0. So that's a very simple form of verification problem, but I call it the canonical form because although this formulation looks very simple, actually we can cover a lot of different scenarios. This stop sign is just like a toy example I made, but actually there are many other examples we can do. For example, in the stop sign, we are trying to show that there's no cell example. But for another scenario, for example, if you're using a neural network controller to fly a drone, and you're going to prove that okay, this drone will always be able to stabilize, and you want to do stability analysis, then the specification would say okay, would say this drone is stable or this drone is safe, and you can equivalently written as some function fx greater than 0, just depends on how you define that function, and you want to show that fx is greater than 0, no matter how the drone starts. For example, you can start the drone from different angles. So this is a set of inputs you need to consider. No matter how you start the drone, eventually it will eventually stabilize. Also, if
Can
you're
I ask a quick
considering,
question?
sure,
For example, for this drone stability,
sure,
we know if it exists a Leopold function,
yeah,
then it is stable. Now the
right,
question is, for an arbitrary nonlinear system, there's
right,
no known method to find the Leopold function.
right,
Linear system, yes, you can calculate right away. So now the
exactly,
question is that, does your research invalidate with this long-held proof?
right,
Basically, say there's a hole in the fundamental stability theorem.
right. I totally agree.
If they say no, then the
Uh,
question is how to find the fx is the challenge,
right,
right? So basically, you
right,
can say, I don't need the opponent function. Okay, then you will revolutionize the stability theory. Another one
right,
is your fx is a Leopold function. Then you find a method to find the Leopold function in
right,
general. Then you revolutionize the stability control.
yeah.
Or
I,
you say fx is correct, but you may not able to find it. So then basically you're consistent with what is known. Now,
exactly,
since the stability function is a graphical theorem proof, so it's not limited to stability. So a lot of
right,
time, the challenge is say there exists as fx, but we may not know how to find it.
right, exactly. Yeah, I totally agree. So the challenge you mentioned is a great challenge, and that's something I'm currently working on actually. And as you mentioned, usually theoretically, okay, if you can find a optimal function and you can prove this condition, and you know, okay, this is stable. But as you mentioned, this is a nonlinear system, and you are probably also using a neural network controller, and so it's really hard to find the optimal function. But actually, in the later part of my talk, I will briefly mention one of my recent work. Actually, we use learning-based approach to find a neurally optimal function, along
Okay,
with a
I'm looking
neural network
forward to,
controller.
yeah, okay, thank you. I'm really interested to hear how you find the Leopold function
Yeah,
in a nonlinear
yeah.
system.
Yeah, thank you for the question. That's a very good question. That's actually a direction I really want to work on. Currently working on. Actually, I'm really interested to solving that problem.
Yeah,
So we have
I
some
want to talk
issue.
to you.
Yeah,
Maybe we could offline, we can talk more. That's a
yeah,
very
sure.
important problem when we try to use AI control things. The
Right,
AI
exactly.
fundamentally is a nonlinear control.
Yes, I totally agree. Yeah, thank you for the question. Yes, cool. And so here I just want to mention that okay, this formulation looks very simple, but actually it can cover a lot of things. You can define the fx differently, and you can verify different kind of things. And how to find this fx actually is another challenge, just like Louis mentioned. So this is actually how to find this fx for your system, right? And also, when after finding, you want to prove that it's greater than 0.
Now,
Sometimes it's
also that I would make one more comment. So the fx has to be differentiable, or at least the moving average has differentiable. Basically, you need to satisfy the property of, and then it has to be decreasing, right?
right. Yes.
Otherwise, it does not converge.
Right.
So that means there also the fx requires basically whatever the opponent written down, sort of differentiable and decreasing. As it was generalized, you can say you go up and then decreasing, but the sum of the Liopold function over a window is decreasing. Okay, you can have temporary
Yes.
increase in energy. So anyway, there's a lot on. So the question is, the Fx, at least in dynamic system, it requires a certain form. Let's say if Fx is not monotonically decreasing, then it is not even decreasing over a moving window. Then we know it cannot be stable. So there's a bunch of specifications.
Right.
So your neural net also find all the constraints and check it.
Yes. Oh, that's
okay. I will probably I will, but your work is very interesting. That's why I asked. Now, one last question.
Yes.
For the stop sign, essentially you said is the disturbance or attack is over a certain geographic area,
Right.
then it's okay.
Right.
So in fact, that's a great idea. The question is, what if, for example, I put a lot of dots, random small dots on the stop sign, and then the whole stop sign area was attacked, and then for human, there's no problem, right? You just put some dot on it. So does you handle this, let's say, whole area attack?
Right. So yes, it totally depends on how you define the set of inputs. The inputs can be there are different kind of threat models basically. For them here we consider a threat model where this is a patch based attack, so you just attack perturb a little patch. But there's also
I understand the patch attack. So how about full area attack?
Yes.
That means I put some small dots all over the place.
Yeah, full area is also possible. That's called the L infinity norm attack. Basically, you can perturb every pixel, but you can only perturb a little bit. So of every pixel. So there are different kind of perturbations you can add here.
Now,
but basically,
if you said the total perturbation is small, then you don't need a patch attack because it covers the patch attack. Patch attack is a small case of limited perturbation of pixel.
Yes. I totally agree.
Will you talk about this more general later in your presentation?
So in my talk, I will assume the easiest way to understand is basically you can perturb every pixel, and for every pixel you have a perturbation bound. Basically, you have a constraint on X, element-wise constraint on X, right? That will cover both settings. If you have the patch attacks,
essentially what you said is the sum of perturbation is more than some threshold.
Right. Yes.
Yeah. So and that covers many attacks.
Oh, sorry, what attack?
If you say sum of the perturbations, the summation of the perturbations, that's one limit, and then it will be cover a lot of special cases.
Right. Yes.
And then you need to probably exclude something. For example, I change the stop into say some other thing, say some other symbol. Now the total pixel alteration may not be a lot.
Right.
But probably that attack will succeed, or at least from a human perspective. You say, oh, that's not a stop sign because it doesn't have the stop on it.
Right.
So the question I think is going back to how to define the Fx rigorously. And so that it doesn't have too many corner cases.
Right. So mathematically speaking, the easiest way would be you have to ensure the perturbation is small enough in the sense that you will never be able to change the stop to something else.
Yeah. So
otherwise,
all I really try to say is the word stop. The small is hard to define. You can include the number of pixels and the intensity change. And if the pixels form a particular word, English word like stop, then we need to define what. Like I said, if you have a symbol X, and then not X. And a not is very small, simple. It's just a tilde, right? If change, you know what I mean? So
Yep.
sometimes you change one symbol, then the entire semantic go opposite. So now so if I big sign, it says stop, and then not stop, of course, it doesn't happen in stop sign. So what I really try to say is there are certain small but fundamental important, just like a symbol A
Right.
and not A, just small changes of the
Yes,
pixel.
yes. I totally
But
agree.
then the question is how to define the meaning of small disturbance. We cannot just we just cannot count the pixel alone.
Right. I totally agree. So the pixel assumption we are making here is just a great
Just to make life easy, I
simplification.
understand that. I
Yeah.
understand that. It's just illustration. But I want to
Right.
think about that. I want to say is the trait of fx may not specify fx. It will be context dependent.
Right. Yes. It'll be
Sorry to
context.
interrupt. I think because like the time is limited, so maybe if the question like goes long and long, you can ask like at the end of presentation for
Yeah.
like
No
audiences to
worries.
have
No
to.
worries. Yeah. I can
I'm
always go
sorry.
faster. Yeah. No worries. Yeah. So those are very good discussions. So
Thank you for consideration.
yeah. So yeah, this is a mathematical problem we want to solve. It looks pretty simple. This problem is challenging just because fx is a neural network function. So it's a function involving neural networks and potentially other non-convex functions. So overall, it's something like this, and you cannot easily solve it because technically you just need to find the minimum of this function and see whether that minimum is greater than 0 or not. But this is actually challenging because of the this non-convexity. And there are several ways to solving it using existing solvers. For example, if fx is just a relu neural network, then there are papers discussing linear programming formulation, semi-definite programming formulation, mixed integer programming formulations, and so on. But all those methods have their issues. So they are usually not very scalable because if you imagine your fx neural network and you want to formulate as a linear programming problem, for example, then every neuron becomes a variable in your formulation, and the number of variables equals the number of neurons. Number of there are also integer variables if you're using the integer programming formulation. That equals to the number of ReLU neurons if you have ReLU network. So in that case, we will potentially have millions of variables, and some of them are integer variables. And that will be really hard to solve. And if you're just using existing solvers, what you can do is a few thousand neurons at the most, and that greatly limits the scalability. So you cannot use those existing solvers to solve large-scale verification problems. And but back to deep learning, if we think of deep learning, what people are doing is they never use those kind of solvers in deep learning. They use forward propagation, backward propagation. Those are famous algorithms to actually to propagate features and to get gradients. And propagating things are super fast on neural networks. And so the insight here is we don't want to use those solvers to solve this verification problem, but we want to do some propagation because propagation is really fast on neural networks. So that inspires the algorithm Huan I developed for neural network verification. This is basically, we call it a linear bound propagation algorithm. What it does is actually it defines a linear bound for this nonlinear function. So even if this nonlinear function is very hard to characterize, but if you once you find a linear function to bound this nonlinear function, you can actually you have a lot of good properties. You can use this linear function to prove a lot of properties to make things much more simpler. And the way of calculating this linear bound is by propagating some linear inequalities, just like how we propagate the gradients through the neural network. And I will briefly show you how that process is done. But basically, by propagating the linear inequalities, what we can do is to get these linear bounds on neural networks, and we can use those linear bounds to do formal reasoning of neural networks. Those linear functions are much easier to handle. Oh, sorry. So here, after let's, for example, for back to the stop sign image example, if you get this linear lower bound, what can we do? Because we want to prove fx is greater than 0. If you don't know how fx look like, of course, this is just a one-dimensional function. As an example, I can plot it, but if fx is 10-dimensional, you cannot really see this function, so you cannot really prove this easily. But if you know the linear lower bound of this function, you can prove that easily, because you can easily prove that this linear function is greater than 0 over this set S. So that's easy. So the question is just how to find this linear bound effectively. You can find a guaranteed lower bound for neural networks. Then you can use this lower bound to do a lot of things, such as proving this stop sign is always a stop sign. So basically, you check the lower bound is greater than 0. That's sufficient for this verification problem. So I will quickly show you how the propagation process works. So this is a very simple example of a neural network. And we have nonlinear layers and linear layers. Nonlinear layers, let's just assume this is a regular neuron here. Linear layer basically is just a matrix multiplication, which are super simple definition. And when we are talking about linear bound propagation, we basically want to propagate the bounds through the linear layers and also through nonlinear layers, and I'll show you how that was done. So before we start bound propagation, what are the linear bounds? So those are basic linear inequalities. So let's see the output of the function if fx. And fx, let's see, we have a linear inequality between fx and some intermediate neuron, these three. So this is just a linear inequality we have. Let's assume we already have this linear inequality. So because this algorithm actually works recursively, so just let's assume we already have this linear inequality for fx and z3. And so this is basically a linear function. And what we want to do is we propagate this linear function through this layer to get another linear inequality, but we change the variable from z3 to z2. Once you can do that, you propagate the bounds through the network. So what we actually are doing is just trying to change the variables, and this is super easy for linear layers. So this is a linear inequality we have, and you just plug in the definition of this linear layer. Z3 equals to W2, Z2. This is just a matrix multiplication. Just plug that in, you get another linear inequality that is still a valid linear inequality. But now the variable changed from Z3 to Z2. And you can imagine if I keep going this process, I will eventually reach the input and I can get a linear bound for fx with respect to x. But the challenge is, of course, how to deal with the relu neurons, right? Those relu neurons, they are not a simple linear function. So you have to somehow still propagate the linear inequality through the function. And to do that, we will have to use some tricks, right? So here you can imagine. So the overall goal we want to do here is we have this linear inequality on the right hand side. We want to get another linear inequality on the left hand side, but we are changing the variable z2 to z1. But the relu is a nonlinear function, but the high level idea is I can use linear bounds to bound this linear function, so I can still propagate the linear bounds through. So eventually I still get a linear bound for fx with respect to z1. And how that was done? So actually what we are doing is basically just the linearly bound relu function with one linear upper bound and one linear lower bound. So for other kind of nonlinear functions, actually you can do that too. So we can actually handle a very general class of nonlinear functions, as long as you can use linear functions to locally bound those nonlinear functions. Note that this bound is only need to be valid locally, because we assume that we have something called pre-activation bounds. This pre-activation bounds basically tells me, okay, what is the range of the relu function between the range of the relu function between this value and this value. So then you can use linear function to bound relu function. For other function, you can do the same, as long as you know the pre-activation bound. You can locally linearly bound this function, this nonlinear function. And how to find the reactivity bounds, I won't go over all the details here, but basically we will still use the Cron algorithm to get the reactivity bounds by just applying Cron. By treating this neuron as an opposite neuron, you'll get the lower bound and upper bound for this neuron. So you'll get reactivity bounds for that. And the mathematical detail would be like, how to propagate the linear bounds through this layer. What you had on the right hand side is this inequality. You would check, actually you have some linear coefficients multiplied on the term z2, and you would basically check whether these coefficients are positive or negative. If the coefficients is positive, then you choose the linear lower bound. If it's negative, you choose the linear upper bound. Basically, you want to choose the bounds conservatively so that this linear inequality still holds. That's how we propagate these bounds. After you do that, you plug in these linear lines, either this green line or this purple line, into this function, and you're replacing z2 with a linear function with respect to z1, basically. After you do that, you get another linear function with respect to z1. So that's how we propagate the linear inequality through nonlinear layers. So basically, the high-level idea is you want to first linearly bound the nonlinear layers, and then you can conservatively choose either lower and upper bound, and then propagate that linear inequality through. So overall, the algorithm works like this. So you have to start from something. We'll start from the last layer, and from last layer, we have an equality says that fx equals w3 z4. Z4 is basically the activation function. It's a feature after the last regular layer. And by definition, we know this definition of this linear layer tells that fx equals to w3z4. This is the starting point. And now you propagate this inequality through every layer through the network. We know how to propagate this through the through regular layer, and we also know how to propagate through the linear layer. And we just keep propagating this process until you reach the input layer, and then you'll get a linear bound for the function fx. This is how this algorithm works, and eventually it tells you is basically for a neural network function fx. I can give you a linear function that provably bound this neural network within the perturbation set S under consideration. And also this entire process is done by propagating some inequalities through the neural network, and that can be done pretty efficiently, and this can be implemented on GPUs, and so you can actually do the calculation pretty quickly. So the complexity you can imagine is kind of similar to backpropagation because you're just propagating some things through the backwards throughout the neural network. So, but of course, this is just the simplest version of the algorithm. During the past few years, we have done a lot of improvements to make the bounds as tight as possible, because if the bounds are too loose or too conservative, it won't be helpful. So particularly, we, for example, study optimization-based methods, branch and bound, and cutting plane method, and so on, to make the bounds as tight as possible. And we also studied training-based approach on training neural network to make those bounds tight. And we're also trying to make those kind of bound propagation to general neural networks such as transformers and general architectures, and we can also handle Jacobians and so on. So basically, I just want to show you how well this thing works compared to the traditional solvers. For example, if you have some small neural networks with just 5K neurons, this is very small compared to the models people are using today. So what we can do is we are reporting this metric called number of percentage of images verified. Basically, you're giving a test set of images, so you want to verify how many of them you cannot find adversarial examples. And the more you verify, the better you are. And you compare, so this is the initial Cron algorithm we have. Actually, this is very fast, but actually this is also pretty weak in some scenarios. But during the years, we have improving the algorithm over time, and the latest version can already actually prove almost all of the images. It's very close to the upper bound in this test set. And on the other hand, if you look at other methods, that linear programming, semi-depth programming, they're doing okay if you're looking at the percentage of verified images. But if you're looking at time, I only plot the linear programming time here because it can finish within a few minutes. Integer programming and the semi-definite programming, they would take in the order of hours or days. So to solve the same kind of problem, and you can see actually they're actually weaker than our method, and we only take maybe 1 minute or so, and we can solve more images than the optimization based approach. So overall, we are seeing like 3 orders of magnitude speed up for this kind of problem that really enables practical verification. Because if you only have things like integer programming solver, semi-definite programming solver, then formal verification for neural networks is never a realistic thing because it's just too slow. It can take 1 day to verify a single instance, and you see it's also not the strongest one so far. So and of course we there are a lot of algorithms going on, but I just introduced the basic ideas behind those algorithms, and but I want to tell you that if you want to use neural network verification, you don't really need to implement all of those yourself because those are fairly complex algorithm. We have implemented them into a toolbox called Alpha Beta Cron. So you can check it out the toolbox at avcron.org. And actually, we were participating in the verification of neural networks competition in the past 4 years, and we were always ranked the top one in the past 4 years. And so those are just some statistics from 2 years. And you're seeing we are actually outperforming the verification tools and algorithm built by many other universities, and we are always achieving the highest total score. I didn't show 2023 and 2024, but roughly the numbers look like similar, so we are still ranked at the first, outperforming many other tools. So those are the high level ideas of the algorithm and the framework and the tool. And now I think today I want to spend some time on discuss some applications on actually applying this verification toolbox to neural network controllers and also neural network dynamics models, and see how we can address some challenge like Louis mentioned earlier, actually, for example, how to do the optimal stability analysis for nonlinear systems. Of course, I can only cover some high-level ideas today, but I will leave all the links to the papers, the titles there, so if you're interested, you can check them out. So first, the easiest thing would be the reachability analysis of neural network controllers. This setting is simple. Let's consider if you have some agent start from some certain state xt, and you have some neural network controller, and you also have some dynamical system. So this could be a nonlinear dynamical system, and this is a nonlinear neural network controller. And given a current state, the controller basically calculates some action, and based on the current state and the current action, the dynamic system will basically move the system to the next state. So that's a very simple setting. And this reachability analysis basically gives a problem where you start with you start the agent with some start set. So let's say the robot is start moving from this region. And after the first step, because you start the robot with a set of possible locations. After one time step, the possible locations will basically be this box. And after three time steps, 4 time steps, the possible locations of the robot will be possibly become larger and larger. And we want to show that this actually you always want to avoid some obstacle. For example, this is an unsafe region. Or you can potentially want to prove that eventually the robot will reach some destination region. Both can actually be proved using the Alpha Beta Cron tool we developed. Just to transform this formulation to the optimization problem we discussed. So we basically define a function fx. Here xt plus 1 equals to fxt. Of course, this function f is a combination of a controller, also the dynamical systems. but we can actually handle that general function. So the bound propagation algorithm we discussed can scale beyond to just the neural networks. We can also handle other mathematical functions involved in dynamical systems. So here you can just say, okay, we have function fx that involves neural networks, and that gives you the next state of the system. And what we can do is, if you view the next state xt plus one, you can calculate the element-wise bounds for every dimension as the two optimization problems, right? So for example, if you just look at the jth dimension of the next state, you can minimize over that dimension given that xt belongs to the initial set xt, or maximize that dimension. And of course, this minimization or maximization problems, they are non-convex and you cannot solve them exactly. But using the bound propagation algorithm I introduced, you can actually find lower bound or upper bound for this minimization or maximization algorithm. And eventually you can find basically a box that covers a reachable set of the neural network. And what if you find out, okay, the controllers are the controller is not safe? Let's say after you calculate the reachable set, found that, okay, here actually it may potentially hit this obstacle. And if that happens, what we can do is actually to train this controller to make it satisfies our safety constraints. What the insight here is, once you calculate the reachable set, you will have these crown bounds to actually lower or upper bounds this function representing, for example, this dimension of this box. And these functions actually, when you're doing the bound propagation and calculates this inner lower bound, these inner coefficients actually they're differentiable functions of model parameters. So that means we can potentially actually optimize the neural network to make this bound tighter. So the idea is, let's say you originally have this lower bound that does not satisfy your requirement. What we can do is we can actually use gradient descent to just optimize W, so that we can change this controller to actually make the bounds moving up. So when it moves up, the bounds become tighter. So that means this red box will become smaller. So that also means we will not hit this obstacle. So of course, in our paper, actually we do more than this, but this is just a example of I just want to show the insight here. We can actually train the controller guided by guided by verification, so that we can actually combine training with verification and train the controller guided by the verification bounds. So another interesting setting we considered was the so-called backward reachability analysis. Basically, given some current state, right? For example, you're sitting at this obstacle. I want to move one step backward or two steps backward to figure out all the regions that can potentially lead to this obstacle. If I can figure out those regions, then I know those regions are unsafe. Of course, here you want to find over approximation of this region, so you don't want the robot to sit in any of those regions. So if you're in these regions, that means after 3 steps, 2 steps, or 1 step, you may potentially hit this obstacle. So this is called the backward reachability analysis problem. When you actually start from the obstacle and you want to trace back and see which are the reachable regions. So then here is the optimization problem just changed slightly. Here the constraint is added on the next state or the output here, but here you want to minimize or maximize the input states, and you can still use the verification techniques. Here I will not introduce the details. If you're interested, you can check out our papers. We actually developed a modified bound propagation method called Prof. Actually, we can actually propagate those reachable sets in the backwards manner. And this is some comparison of how tight our bounds are. So for example, this is the obstacle. If you calculate 1 step back, 2 step back, we're doing over approximations, and we're comparing to empirical sampled points. Here, you can see actually we are pretty, we are getting a pretty tight over approximation of possible reachable set. And if you compare to previous baselines, what they had is actually very loose, very large boxes that are not helpful. It's too conservative. So on the other hand, another problem is all the systems I described are discrete time systems, but there could also exist continuous time systems, where here I assume you have a neural network controller. The controller is dealing with a dynamical system which is continuous time. So here you have the controller has some control frequency. So the controller is sampling this dynamical system after every delta t time, and the controller will output some action that is held within this delta t time. And the dynamic system will basically evolve during that delta t time by some differential equations. And so now the reachable set is not just a bunch of box, but it more looks like a tube, because during this delta t time, actually the dynamical system, this differential equation gives you where the next x is. And in this setting, because you also have ODE here, that makes the problem more tricky. And we're developing a new tool called Cron-Rich, actually can do reachability analysis to this kind of neural network controlled systems. And we are using a hybrid approach. We're using Cron for propagating the bounds through neural network controllers, and we're using another toolbox called Full Star for propagating the bounds through the ODEs. So eventually we can analyze the entire system very efficiently. So we're participating in the ArchComp, another competition on verifying hybrid systems. And this is actually the first time we're participating in this competition, but actually we're solving more instances than the existing toolbox that has been participating for many years. And if you're interested, this is the link to our toolbox, and this is actually a newly developed tool this year. And finally, all of those are reachability analysis, and we want to go beyond reachability, and we want to reason about the behavior of the system in an infinite time horizon. And in that scenario, we have to use the Lyapunov theory. Basically, shows that there are certain invariants on the system, such that once the time step move forward, this Lyapunov function is always decreasing, and we will reach zero at the equilibrium point. And for non-equilibrium point, it's always positive. So this is from the traditional control theory, but the issue is actually how to find the Lyapunov function, like just Louis mentioned at the beginning of this talk. So the challenge here is we have a nonlinear system. We are assuming this dynamical system is nonlinear, and also we have a neural network controller. If the system is linear, and you are using a linear controller, and the problem is easy, and you have a closed form solution, and you can use LQR, and you can use closed form solution quadratic Lyapunov function. But here the challenge is the system is nonlinear, and we also have a neural network based controller, and you cannot just derive a Lyapunov function manually because of the complexity of the system. So the way of tackling this problem is by seeing this entire problem as still as a big function fx to verify. So in our paper, actually, we parameterize the function v such that it already satisfies the first and the second condition by construction. So we only need to verify the third condition. And eventually, if you just apply alpha beta cron based neural net verification, you can actually prove that the Lyapunov condition is true by just checking within the region of interest. This condition is true, so that means within this region, actually, the system will actually converge to the equilibrium point. What I didn't mention here is actually in our paper, we also have a training method actually to train the controller and the Lyapunov function together. So even initially you have you initialize the controller and the Lyapunov function with some random neural networks. But after training, actually, you can find the working controller and the working Lyapunov function that actually works and also can be proved to be stable. So these are some results we showed in our paper. So there are some other baselines. For example, you can use sum of squares based method or integer linear programming based method to calculate region of attraction. But our method actually gives you the largest possible region of attraction so far. And the challenge here again is this is a nonlinear function, nonlinear system, and we are not hand deriving a Lyapunov function. And the controller and the Lyapunov function, they are jointly learned and verified, and we can show a reasonable large region of traction here. So I want to mention that if you have some new applications you want to apply our methods, so I introduced some applications. But if you have some ideas, let's say you are dealing with some neural networks and you want to give some bounds, and we do have this library built uh, 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 that you can use directly by just define your computation function and to just call the library with the perturbation set S, and you can get the upper bound and lower bound directly, and everything is GPU accelerated and it's pretty fast. And I want to make a little bit comments on the open challenge on learning-based approach for control. Uh, in traditional control theory, you have to solve a bunch of optimization problems, and in many scenarios, there's no closed form solution. And to deal with general nonlinear systems, it's really difficult, and you have to rely on some linearization or some different kind of tricks. But if you're applying learning-based approach, and we hope to find more performant controllers, and we still want to get all the good guarantees, safety guarantees, stability guarantees, that's where neural net verification can help you. But there are definitely still many open challenges, like how to handle uncertainty in the system, disturbance in the system that wasn't handled in my paper, and also how to scale up to very large neural net controllers and high dimensional systems, and how to figure out the best training scheme, right? Because during the development of our method, we actually found the training is quite tricky, because if you actually want to train using learning-based approach to find a working controller along with the working output function, it's actually pretty challenging. So I just want to mention in this area, there's still a lot of unsolved problems, but now we have the toolbox that can solve some of these problems, but there's still many open challenges. Finally, I think I will briefly mention my recent work of also using neural net verification techniques to do model-based planning. Particularly here, we are planning using a neural dynamics model. So this is actually the real robot experiments using our algorithm. In our setting, actually, we first train a neural network dynamic models. Basically, there's a model of the system that is done by a neural network. So here you see there is a T-shaped object that's moved by this robot arm. So how the robot arm knows how to move this T, because it has a model, and the model is a neural network. So the model can be easily trained by just simulating the system, and you have some trajectories, and you can basically reduce some loss function between the current state and predicted state. So basically, there's a neural network I denoted as FDYN here. This is a neural dynamics model which can predict the next state of the system given the current action. So this is a non-trivial task, because if you look at the T-shaped object here, it's not like you're just pushing a box or a ball, because the T has a different contact points. If you push here, actually the T would rotate. If you push here, the T would actually shift. If you push here, there's no impact. If you push here, it could both rotate and shift. So there are quite complicated dynamics here, and we want to learn that dynamics first using neural networks, and then using these neural networks to do planning. So as you guys may know, so in model predictive control, basically you want to you want to decide some cost function of your planning, and basically you want to minimize this cost function by minimizing certain by choosing the optimum actions. So here the objective is pretty simple. So basically you just define the cost function over the t steps, and each step is predicted by this neural dynamics model, and eventually you are facing the optimization problem very similar for what we had before, because here the actions usually you have some constraints on the actions. You cannot apply like infinite force to the controller, and you have controllers some constraint over the actions. And if we define all the action vector over all the steps as a big variable x, then we are essentially minimizing the function fx. This fx represents this summation, and this is again a non-convex and highly complex function, because this involves the neural networks, actually involves multiple neural networks, because each step you unroll your dynamics, you have to use this you have to use this neural network, and you have actually have t dynamics models inside this summation. And how we solve this problem? This problem it looks very familiar to the verification problem we are solving. And here we want to, but here instead of finding a lower bound or upper bound of the function, actually we want to find the optimal action sequence or the optimal solution of this function. And that's a little bit challenging because the verification algorithm discussed can only give you a lower bound. It does not give you any solution. But on the other hand, you can just randomly sampling a few points on this function. You can actually using those random sampled points to give you some solution, although those solutions can be far from optimal. So the idea here is we are going to use the verification bound to guide the search of the optimal solution, and I'll quickly show you how that is done. So let's start with some random sampling. If you just start with some random sampling on this function, you can find you won't necessarily find the optimal solution. The optimal solution basically means the optimal planning, the optimal action for this robot. But here, if you just sample a few points, you can find the upper bound of the optimal solution. But you cannot really find the true optimal solution. You can just find the upper bound. So this is gonna be a worse solution, and then the best solution. But it's guaranteed to be upper bound. And now we introduce the process of branch and bound. So branching, in the branching step, we are basically split the problem into two sub-problems here, C1 and C2. And now we are applying cron, which basically gives the lower bound for the two sub-problems. So on the left-hand side sub-problem, you get a lower bound like this. On the right-hand side sub-problem, you get a lower bound like this. So why those lower bounds can be helpful? In the next step, we will see that actually for the left-hand side, for the C1 part of this function, you'll see the lower bound like this. It's actually always greater than the current best upper bound. Since the lower bound is greater than the upper bound, that means there does not exist any solution in C1 such that the solution is better than the current best solution. That means you don't need to search in the C1 region at all. You can just remove C1 region and just look at the C2 region of this function. That allows you to do more sampling, and because now the region is smaller, your sample would be more effective. That gives you a tighter upper bound as well. So your upper bound improved by sampling in just this smaller region. And we can just keep doing that process. For example, here, you further divide that region into C3 and C4, and you're getting near lower bounds for those two regions. You will see, okay, in the region C4, the lower bound actually is going to be worse than the upper bound, the optimal current best solution. That means you don't need to search in the region C4 anymore. You just need to focus on region C3, and that region becomes smaller and smaller, and you'll be getting closer and closer to the optimal solution. So after to that, you can actually get a pretty good solution compared to the previous method. So here is how the objective is decreased during the process, and we are compared to some popular model predictive control methods. So here is a sampling-based method called MPPI, and you can see, okay, it can reduce the loss function but eventually it will not get the optimal solution. You can see here this T shaped object will not move to the exactly to the target. There is always some small difference. So because the number of steps we can move is fixed. Let's say we can only move the robot arm by 20 steps. Then you have to reach the goal by within 20 steps. Then you have to have some optimal control action. That's in our case, we can see the action is actually pretty optimal. It just moves the T very stably, and also it can go over pass over the two obstacle and not have a collision with the obstacle, and also can reach the target. There is some additional results on the T and also on some other environments. And here I just want to show you the algorithm actually has been demonstrated on a real robot. So this is just not just run on simulation, but actually we actually also run it on real robots. You can see so our planning actually gets you to the destination, but if you're using a baseline method, actually sometimes it cannot find the solution because it just involves very challenging planning and optimization problem here. Cool. I think that concludes my talk. So today I talk about the concept of formal verification of neural networks, and I discussed the alpha beta quant framework of propagating these linear inequalities of on the neural network to get approval bounds on neural networks, and also talk some applications of reachability and Lyapunov stable analysis on neural networks, as well as using verification inspired method for planning with neural dynamics models. Thank you, and I'm happy to answer any questions now.
I think there is a question on chat.
Sure. Yes, I saw the question. The importance of training, it seems that the performance of neural network controllers should depend on the data set used for training. How one can quantify the effect of the training data for the reachability problem? That's a very good question. Actually, the data is very important. And usually the best way of construct the data set actually is to construct the data set on the fly. So, like for example, for the setting of verifying the Lyapunov function, the way we used in our paper was to actually during training we will find some data point X, basically some state of the system, that does not satisfy this condition, and we basically add those points to the training. So we want those points to satisfy the Lyapunov condition until we cannot find any counterexamples. If you know that technique is called a counterexample guided synthesis. Actually, we'll keep trying to find a counterexample in this case, and we're adding all the data points that does not satisfy the Lyapunov condition into the training set, and we hope that all the points can satisfy the condition eventually. So the training set actually have to be created dynamically rather than have a fixed set of training data.
Okay, thank you for that. Can you hear me?
Yes, I can hear you.
So when you say to add those points where the Lyapunov condition is not satisfied,
Right.
doesn't that imply that you'll make a system visit possibly unsafe parts of the state space? Then how is the safety guaranteed?
So in this particular work, we're only deal with stability. We're not dealing with safety. But I would imagine, so you can combine the Lyapunov function with barrier functions and to guarantee both. But for this particular work, we just work on the Lyapunov functions.
Okay, thank you.
Thank you. Any additional questions?
Yes. Oh, go ahead.
No, you go ahead.
No, I was going to say that was a great talk. One of my questions was going to be on piecewise linearity, and you kind of got into it on the training part. I guess my question is on the early work where you're talking about, hey, I have a set, I found bounds. It would seem that those bounds would be pretty conservative. So my question was, hey, breaking that up into piecewise segments. But the follow-on question as far as conservatism is, you can't sample or you can't test every point in that set.
Right.
So are you somehow doing like a convex hull and then applying the linearity to ensure that every point is covered in that set, or how are you covering the entire set?
Right. So, yes, those are very good questions. First, I think the second question is probably easier to answer. So because like during the bound propagation process, we're always maintaining a linear inequality, and eventually, we guarantee this is guaranteeing a lower bound for this function within this set. So we are always considering a set in this problem. So this problem is challenging, as you mentioned, because we are dealing with a set, right? So the input usually for a neural network, if the input is single data point, the output is also single data point. That's very easy. But here, the input is set. We are always considering a set of actually a set of inputs, and these bounds have to hold for a set of inputs. And eventually, as you mentioned, it would look like a convex hull or something. So if you're just applying just one single linear bound or one single linear upper bound, that would be look like a convex hull of the graph of this function, because you are bounding the lower upper bound using two linear functions. But as you mentioned, so what we can also do is to actually I think you mentioned the piecewise linearity or something like that, right? So what we can actually do is actually by splitting the region into two small regions, basically we can do branch and bound, so that actually inside each region we can use the linear bound. So eventually we can get a much tighter overall bound. So that's something I didn't talk in detail today, but we can in our verifier actually you see we have beta cron actually essentially is doing branch and bound, and eventually actually for example to verify the left move control problem, we actually have to split the region into maybe over 10 millions of smaller regions. But all that process is done automatically, and that is also done very efficiently because all the 10 million regions are evaluated on GPUs. And because the network are not that large, the GPUs can calculate maybe 10,000 sub-problems within a second. And it just in total we just need a few hours to verify all the 10 million sub-problems.
Okay, great. Thank you very much.
Thank you.